in this notebook, we'll put together the objects that we have defined as compositional tools, notes, rests, and sequences, and start writing some music, both melodies and also some polyphonic exercises. Now, this notebook is based on the lecture about combinations, and in that lecture, we actually considered and discussed various ways of using randomness or selected probability distributions to create melodies or harmonies. And so we will start from just a random musical model where we introduce a generator for random numbers and refer to the NumPy numerical library for Python if you want to learn more on how to define these generators, but suffices here to have this particular cell that initialize a random generator. And here in this line, we are generating 1,000 random numbers, and we are plotting them here, and you see how this distribution looks like. Of course, anytime you regenerate recall this function, the distribution will change accordingly. So we have a way of generating random numbers. Now, how do we put together this and create, for instance, a random sequences of notes? Again, we use our tools that we have discussed previously, the objects rest, note, and note sec as a sequence of notes. Now, here I'm introducing a new function that generates random notes in a sequence, and I'm building this through this loop where I'm adding as arguments for each node that goes in the sequence a definition of pitch, octave, duration, volume, and build the node object that then goes into the result sequence. So I do this. This function accepts a pitch list, an octave list, a duration list, and so on. So here I have my lists in the arguments. So I take all the nodes between 0 and 11, so the whole chromatic set. I want a range of octaves between 5 and 7. So from the central C to 2 octaves above, and a series of durations that here is 1/4, 1/8, and 1/2. 50 is just a volume for the MIDI. If I want to generate a MIDI object, MIDI file afterwards. I do this, and the list has been generated, and here I can display them in the notebook. It will take some time, but here it is. Not only that, but here in the display notes, I added another argument that is the show. And so here I'm requesting the code to generate a MIDI file that then I can listen to, and we can play it here in the notebook. You can explore other possibilities, change the arguments, the parameters, and see what you can generate. Not only you can generate melodies, you can generate also polyphonic structures. So here I define 2 different sequences of notes with different octave ranges, but also on the chromatic, using the chromatic scale of the 12 pitches. I define a combined list that has the first part and the second part, and then I can again display note and get a MIDI file that we can play, and this is the result. Some avant-garde piano music here. As a possible exercise here, I'm suggesting to generate the code that I have given you for the generation of a sequence of notes and with different durations, generalize to add also rests with a given probability. So basically what you should do is you go back to this function here and you add in this generation of note sequences an option that if the probability is, if a random number is smaller than say 0.5, so 50% probability, you generate a note, or if it's out of that range, you generate a rest, and you can play with the rest and the relative density of rests and notes and see what happens, both in a single melody and in the polyphonic structure. I will do 3 different videos for these other analysis notebooks, so look for the videos in the other folders for the analysis of scores, where we can use these ideas of randomness in looking at what a composer did in its compositional process. So in the lecture, we also talked about the idea of a random walk. That is a sequence of numbers of positions, say, in this particular case, that's why it's called a walk, that are randomized in a way that each individual position is independent from whatever trajectory that that object has taken before. A typical example of a random walk, for instance, is a coin toss. In a coin toss, probabilities are independent, and every time you toss the coin, you get a different result that is independent from the results that you had before. We can use random walk for generating melodies. Now, of course, the nature of the random walk is that in this particular example, for instance, I start from a particular number that could be a pitch or could be any parameter of the music, and I can increase it by 1 or decrease it by 1 with a random probability of 50%, for instance. So what I get is a very linear melody here, where pitches are separated individually just by a, say, for instance, a semitone, if we use the whole chromatic scale. So in this example, I'm generating a random walk of 100 notes, and you see here that all this, all the melody, the whole melody is comprised of semitone intervals. A more interesting kind of, again, stochastic process that we can consider for the generation of musical objects, musical ideas, are Markov chains that are defined by a transition probability matrix, as I explained in the lecture. And the Markov chain can represent also a random walk if we define our matrix of probabilities in an appropriate way, as in this example here for the simple coin toss. Now, there are a few exercises you can do here. You can check, say, the validity of the random idea, in the sense that we expect to have a number of tosses, heads and tails, that if the transition probability is like 50% for each event, should be actually equal. And you can see here that, of course, this is a stochastic process, so you have to go to very high numbers in order to achieve this equivalence in a way. And here you can see, for instance, that with 100,000 tosses, the sum of all the results, there should be 0 for the exact 50-50 probability, is actually 336, but the ratio 300 over 100,000 is clearly very small. So these are suggested exercises that, to play a little bit with Markov chains. In particular, I would encourage you to look at how the effect of the transition matrix, transition probability matrix in the results. So, for instance, look at the biased coin toss or the persistent coin toss that are defined here. Now, Markov chains can be used, for instance, to generate both rhythms and melodies. And this is an example of an implementation of a Markov chains for rhythms. So here we have a list of durations that we can choose from. And this can be, you can decide your own list to explore the different possibilities. And then you can define the transition matrix that basically tells you what is the probability that, given a particular duration of the value of the note, the next note is a different duration with some different probability. So, for instance, if we look at this matrix here in the first row, it means that if I'm starting with a read that is this one, the first one in the duration list, I have 0 probability that the rhythm is used again, 0 probability that I have a quarter duration, 70% probability that I have 1/8, and 30% probability that I have 1/16. And so this is kind of the way in which this transition matrix probability works. So now we apply this idea, and it's actually very easy to do it using a NumPy function that is called random choice, that basically chooses a particular element of this list with a particular probability, given the probability of the previous event. And then you add this to a list, to a sequence, and then you have a rhythm sequence that is generated by this Markov chain. The same concept applies to a melody, where now the transition probability tells us what is the probability to go from one note of a particular pitch to another particular pitch on this pitch list. And this example is an example that generates something that is kind of a pseudo-Gregorian chant. So the useful and interesting part of using Markov chains for generating melody or rhythm is that you have a choice in the definition of the transition matrix that can reflect particular rules. And so here, for instance, this transition matrix, as is defined here, is based on the transition probabilities observed in real Gregorian chants and summarized kind of a very general way in this series of probabilities of transitions. So if we start from a particular scale here, the Dorian mode of the ecclesiastic modes here, and we use a transition matrix that is being obtained or derived from the analysis of real Gregorian chants in the Dorian mode, then we can generate our own pseudo-Gregorian chant